All right, cool. Let's dive in. Folks like having this walkthrough, so I thought I would do it. Okay. Again, got to see the work to get credit for the skills quiz component, and doesn't help you to know the answers to these questions. Helps you to know how to answer these questions. So let's dive in. Right. At a large hospital, the durations of emergency room visits from check-in to discharge are approximately normally distributed, with a mean of 167 minutes and a standard deviation of 76 minutes. Which interval to the nearest minute contains 80% of durations? We talked about this a lot today, with a lot of different groups. This does not mean which of these has an endpoint at the 80th percentile. We want the low bound to the high bound to capture 80% of the distribution given this mean and this standard deviation. So, the best way to do this, honestly, is to just test these with normal CDF and see which one gets you closest to 80%. So, let's start with C, just because it's nice and in the middle. Seems like a reasonable place to start. We're going to normal CDF that. Our low bound is going to be 70. Our high bound is going to be 264. Our mean is going to be 167, and our standard deviation, 76. Just because I'm such a maniac towards you, I will label my stuff. I'm not going to do the curve, though. And when we pop this in a calculator, what do we get? So we have 70, 264, 167, and 76. Okay, so this is 0.798. I'm going to say we're not going to get closer to 80%. So the answer here should be C. Just for demo, I think this gives one of the boundaries. I think 231 is like at the 80th percentile. If we normal CDF that, and again, I'm going to do this in a different color. Once you have an answer that's this close, you're done. But if we did normal CDF and instead our lower was 103 and our upper was 231, keep the same mean and standard deviation, we get, what is this? 103 to 231. That only gives us about 60% of the values. So we're using normal CDF. We're not trying to figure out what's at the 80th percentile. We're trying to figure out what contains 80%. All right, onward. An infrared thermometer measures the surface temperature of an object from a distance. The measurement errors for one particular model are approximately normally distributed, with mean of 0 degrees Celsius and a standard deviation of 1.3 degrees Celsius. If the temperature of an object is 20 degrees, what is the probability that the thermometer will report the temperature as less than 18 degrees Celsius? Okay, I thought about this one way. Student today thought about it a different way. I'll show you both. Same basic principle. Still with our friend normal CDF. So the way I thought about it was, okay, if the mean of this distribution is 0, right? The errors are normally distributed with an average of 0. And 18 degrees is 2 below 20 degrees. I would need my error to be 2 below. So if I got the average error, I would get 0. But in order to get 18 or less than 18, I would need to be getting an error of I'm 2 degrees below or more. So when I normal CDF that, I'm going to have negative infinity, or an approximation of it, as my lower bound. My point of interest, 0. And this is a little tricky. 0 is the mean here, but 1.3 is the standard deviation. So I need to use 1.3 as my standard deviation. When I do that, Oops. 0 and 1.3. I get 0.0619. Oh, bother. I'm going to delete that and make it be that. Oh, that is what it matches. So that's what the answer is. Another student thought about it as, okay, well, we are at 20. We're trying to see the probability of being below 18. And since we can do this because the mean is 0. So we're not expecting any error. So 20 is going to be at the point where 0 is. So essentially what I've done is taken this distribution and shifted it up by 20. I just added. And what's cool about this is it kind of addresses the idea that we can shift, right? Adding and subtracting affects our means and our values, but it doesn't affect our standard deviation. So we can still say normal CDF, and in this case, we're still at negative infinity. But now our upper boundary is this 18. The mean is now 20 because we shifted that mean up, but the standard deviation is still just 1.3. When you put this into normal CDF, and we've got negative 18, we get exactly the same answer. So either way to think about it is great. Whatever makes the most sense for your brain, do that. All right. Crossed out that. Okay. Nice long questions. Yes, lots and lots of things to read. A study was conducted to test a new style of keyboard in preventing repetitive stress disorders. Volunteers who have had problems with such injuries were randomly assigned to use either a traditional keyboard or the new design. A significance test was conducted with the alternative hypothesis that a smaller proportion, so here's our alternative hypothesis, that a smaller proportion of those using the new keyboard will suffer injuries than those using the traditional keyboard. The resulting p-value was 0.07, which is a correct interpretation of this p-value. Okay, so this again, use your answer choices. Read them all, consider them carefully. Look for what's wrong. The null hypothesis should be rejected. Well, maybe we don't have a significance level. So we're not going to cross that one out yet, but it's not great. We don't really have the support for it. B, the null hypothesis should be, I'm not even going to say that word. We do not ever say this word. Cannot be B, not in a million gazillion years. Okay. There is a 7% chance that the null hypothesis is correct. Not exactly. That's not what our p-value means. There is a 7% chance of getting a difference between the two groups at least as large as the observed difference if, here's the conditional probability, if the new keyboard is really no better at preventing injuries. So thinking about if we were doing this, right, our null hypothesis would be that the proportion, right? So that the P1 would be equal to P2, and I'm going to be annoying here and not define them. Our alternative would be that P1, the old keyboard had a higher proportion of injuries than the new keyboard. So what we're saying with D is, if this is true, if the proportion of injuries with the new keyboard and the traditional keyboard is the same, then we have a 7% chance of getting a difference like the one we got or bigger. And that's just basically what a p-value is. It's the probability of getting a result at least as extreme, and so it's important that it's at least, as the result you got in your sample, given that the null hypothesis is true. If the null hypothesis is true. This is why we do probability before we do inference. All p-values are conditional probabilities. All right. There's a 7% chance that the observed difference is due to chance. No, so this is really like a crummy way of trying to get at this. And then we can't say that the null hypothesis should be rejected because this is not below any reasonable significance level, and no significance level was given. We found something that's a lot better. We could have a significance level of zero point 0.1, in which case this would not, or excuse me, of 0.05. This would be greater than that, so we'd fail to reject. If it was 0.1, we could reject, but we don't know. Okay. 4. For a class project, Charlotte recorded the heights of all 28 students in her class and calculated several statistics. She then realized she made an error regarding the height of the tallest person in the class. She correctly had him listed as the tallest, so that's important, but needed to add 2 inches to his recorded height to correct it. Which of these measures of spread, so these are all measures of spread, must remain unchanged? So which is going to be unchanged? So basically, we have all this data, and then we have Mr. Tall Person. Let's say he's like 75 inches. And now in our new data set, he's actually 77 inches tall. That's pretty tall. Okay, so which of these must remain unchanged? First up, we are taking this further away from the mean. We have some mean, but now we're actually going to increase one of our values. That's going to increase the mean. Because that's going to increase the mean, we're going to increase the mean absolute deviation, so that's not unchanged. And it's going to be further from the mean probably, at least a little bit. So that is going to affect the mean absolute deviation, the standard deviation. And then variance is just standard deviation squared. So that's definitely getting affected as well. The range, well, whatever let's say our shortest person is 5 feet tall, so they're 60 inches. Well, the range has now gone from 15 to 17, so that definitely changed. Our interquartile range is not going to change because we only affected the highest value. So wherever Q3 was, or Q1 was, and wherever Q3 was, taking this value and shifting it a little bit further this way, we haven't touched our quartiles at all. So our interquartile range is unchanged. Okay, good. And Zoom changed all its things. Okay, it's still recording. For a second, I was like, was that actually recording? Because that would be pretty on brand. Okay. Next up, biologists around the world have increased efforts at conservation. Monitoring wildlife populations is important so that appropriate management efforts can be implemented, but such monitoring is often difficult. One study found a cheap and easy way to estimate the number of nesting sites of terns, a type of seabird, by monitoring the number of calls heard per minute. More calls happen when there are more birds, as one would expect. In fact, it turned out that the number of calls explained 71% of the variation in the abundance of nests between breeding sites. Which of the following statements is correct about the correlation between the number of calls and the abundance of nests? Okay. So, first things first. Looking at an answer like E, the slope over the regression line is needed to determine the correlation. I'm not going to say that's always wrong, but it's a really nice friend if you're not sure how to do this to be able to say, oh, well, maybe I just don't have everything I need. That's a pretty good thing to be wary of, right? Second of all, more calls happen when there are more birds. So we would expect, if we thought about our scatter plot, as we move to the right, as the number of calls increase, we should find an increase in the number of nests, right? Something like that. This is going to be a positive relationship. So remember when we're describing scatter plots, strength, form, direction, Sir Francis Drake. So strength, pretty strong. Form, this one looks pretty linear. And direction is positive. Correlation is going to have the same positive or negative value as the visible slope in the scatter plot. So we can get rid of our negative answers. Last but not least, this is a pretty good definition of R squared. The number of calls explained 71% of the variation in the abundance of nests between breeding sites. So R squared is the percent of the variation in Y that can be explained by the variation in X. So R squared is 71%. The correlation is R. So I'm just going to make a little note here for y'all. So this is the correlation. This is something we call the coefficient of determination. Okay, so if R is 0.71, or excuse me, if R squared is 0.71, we just have to square root that. And square root of 0.71 is not 0.71, right? It's got to be 0.84, and it is. So that's why our answer is D. Cool. Number 6. Students in a statistics class, as part of an activity, measured the length of their hair in inches. Summary statistics are shown below. So we've got the sample size, the average, the median, standard deviation, minimum, maximum, first quartile, and third quartile. I guess someone shaved their head. Must be a sports season thing, right? Which of the following statements is true? Again, which is true? Which must be true? Which remains unchanged? You want to check everything in this type of question. 75% of the students had hair at least 18.5 inches long. So 18.5 inches is the third quartile. 75% of the data is below that. So the at least is what makes this one wrong. So that's out. Now, 50% of the students had hair between 9.18 and 29 inches long. It's really appealing. A lot of people pick this as the wrong answer. In part, I think because you're not reading all the choices. So make sure you're reading all the choices. So the mean is 9.18. The maximum is 29. And so there are 50 percentiles between that, but it doesn't mean that 50% of the students. This is why we make the distinction between mean and median as non-resistant and resistant, respectively. So we could have some big outliers or some small outliers that are really pulling the average, the mean, in one direction, but they might not really be representative of most of the hair in here. So it's not true that 50% of the students had hair between the 50th percentile and the maximum. Now this one, 50% of the students had hair between 2 and 18.5 inches long. We're talking about 50% of the students, like the students themselves. Q1 is 2, Q3 is 18.5. 50% of the data is always between these. So 50% of the actual number of students is between Q1 and Q3. So that's going to be our answer. The distribution of hair lengths can be appropriately modeled by a normal distribution. Normal distributions should encompass pretty much all of the data within 3 standard deviations above and below the mean. There's a problem if we say 9.18 minus 3 times 8.91. That's going to be extremely negative, which is going to be certainly painful, if not deadly. Negative hair is not something that is reasonable, so we can't model this with a normal distribution. And then the distribution of hair lengths has at least one outlier. So this is a good little review on outliers. There's a cat being bad. I hear you. Monster kitties. So let's review a little bit on outliers. Uh, so we can use the typical one is Q3 plus 1.5 IQR. Anything above that is considered an outlier. And then we have Q1 minus 1.5 times IQR. And anything below that is considered a low outlier. So Q3 is 18.5 plus 1.5 times 16.5 is our IQR, right? Q3 minus Q1. And what is that? 18.5 plus 1.5 times 16.5. That's 43.25. Our maximum is 29, which is way below this, so we don't have any high outliers. Let's do the same thing for our low outliers. We have 2 minus 1.5 times 16.5. Again, that's going to lead us into negative hair lengths, which is not reasonable. So there aren't any low outliers. More importantly, our minimum is 0. This is going to be negative for sure. That's below 0. So we don't have anything less than 0. Okay, onward. After graduation, you have the opportunity to open a local pizza restaurant. To cover all of your expenses as well as pay yourself a salary, you need an average revenue of $9,000 per month. Anything less than that, and you risk losing your business. You take a random sample of 30 different pizza restaurants, similar to the one you hope to open, and get data on their monthly sales. For the hypotheses, the null is that the mean is $9,000, and the alternative is that the average is greater than $9,000. Now we want to describe a type 1 error and its consequence. Okay, so a type 1 error, again, I sort of think about it as a false positive. You reject the null when you shouldn't. Okay, so the consequences of a type 1 error cannot be determined without a significance level. Again, really attractive if you don't remember, like, oh, maybe I just can't do it. No, you can. Don't pick that one. B, you believe the average sales of pizza restaurants like yours is more than $9,000. Okay, so we're just going to take this in pieces. You believe the average sales is more than $9,000. That would mean we're in this realm. So we have evidence that we can reject the null. So we're going to leave that on the table because in order to have a type 1 error, we have to reject the null. So let's look at C. You believe the average sales of pizza restaurants like yours is more than $9,000. Okay, so again, we would reject the null there. Still in play. Just gonna make a note that we've gone to that bit. You believe the average sales of pizza restaurants like yours is $9,000 or less. That would not allow us to reject the null. So we can't make a type 1 error if we don't reject the null. So this one's out regardless of what the rest of it says. You believe the average sales of pizza restaurants like yours is $9,000 or less, gone for the same reason. Okay. Now we're left with B and C. Let's see which one is actually an error. So we believe the average sales of pizza restaurants is more than $9,000. So you open a pizza restaurant and have a high risk of losing your business. That sounds like a pretty good error. Versus you believe that the sales are going to be more than $9,000. So you open a pizza restaurant and have a high probability of a successful business. That's not a mistake. That's good. We had data that said we should open this. We opened it and our chances of success are good. That's not an error. So it can't be this one. In order for it to be an error, it has to be incorrect. So the only thing left is B. And so in this context, we think we can reject this. We think we're in this realm. But in reality, we might be here or less. And so this is the problem. We have a high risk of losing our business. Okay, onward. I think a lot of people were really close on this one based on the conversations today. A particular crop of one variety of onion has weights that are approximately normally distributed with mean 9.8 ounces and standard deviation 2.1 ounces. How does an onion in the 28th percentile for weight compare to the mean? Okay. I'm going to get rid of dumb answers first, and I'm going to get a little accustomed to what my answers are actually saying. 28th percentile is below average. Average is going to be the 50th percentile. So I know that my 28th percentile onion is going to be below the mean. So A works because it says below the mean. B works because it says below the mean. The rest of these say above the mean. Well, that's just not going to happen. If we're at the 28th percentile, we're below average. Done. We've now taken this from a 20% chance if we have to guess to a 50% chance if we have to guess. That's way better. Okay. So from here, 20th percentile, well, to find a value when we know the percentile, we're going to say inverse norm. So second inverse norm. The area, since we're dealing with percentiles, we just want that bottom from the bottom to the 28th percentile. Always make sure you're labeling. Oh, bad cat. And then we want the mean to be 9.8 ounces and the standard deviation to be not there. Label there. 2.1 ounces here. A very large cat who makes poor decisions is distracting me. I'm sorry. Okay. So this is going to give us the weight of a 28th percentile onion. So area is 0.28, mean is 9.8, and standard deviation is 2.1. If you have one of the newer calculators, make sure when you're working with a percentile that you're using a left tail. All right, so we get that this onion's weight is 8.576. So if we take the mean and we subtract that weight, 8.576, buddy, you're a monster. And we're going to get 1.22. So it's 1.22 ounces below the mean. Now, a lot of folks found a z-score for this. I believe the z-score is negative 0.59. It's not asking for a z-score. It's asking for this in context. So this is kind of like that problem that almost everyone missed, where you got the correct interval for the difference in proportion, but not in numbers of apples. So pay attention to what you're actually being asked to answer. Don't just run on autopilot. All right. Next up, blocking. Woo. A pharmaceutical company wants to test a new cholesterol reducing drug against the previous drug. Good idea. Always test against the standard of care, not nothing. That's unethical. It does not anticipate much association between cholesterol and gender. It does not anticipate much association between cholesterol and gender, but it does anticipate an association between cholesterol level and the amount of exercise a person gets. Okay, so we're expecting exercise to affect cholesterol level. That's what we want to block on. We want to block on the thing that we think might affect what we're studying. So we can make sure that we don't accidentally get like all the people who exercise in one treatment group and all the people who don't exercise in the placebo group or the standard of care group, and confound our results with just the fact that some of them exercise or not. We want to make sure that every block has people with similar exercise levels so that we can assign within each block some of the new drug and some of the old drug, so we can see among people who exercise a lot how does that drug affect? And among people who don't exercise a lot, how does that drug affect? And by blocking this way, we'll ensure that some of the people with our new treatment exercise a lot, and some of the people with our new treatment don't. And some of the people with the old treatment exercise a lot, and some of the people with the old treatment don't. So we're blocking on the amount of exercise, not on gender, because we don't think it's associated. We don't need to block on that. Not going to block on gender. Type of drug, no, that's the whole point. Block on exercise level because it is associated with cholesterol level. And then block on both gender and exercise, no. Blocking on more variables gives more reliable estimates. I mean, not necessarily. Like, we don't think gender's associated. If you were doing this and you had lots of resources, sure, block on a couple different things, make sure you have good representation. But what we're looking here is we want to block on what's associated with it. Okay. 10. A department store has a promotion in which it hands out a scratch card at the checkout register. I'm going to pause for a second. All right. So 10. A department store has a promotion in which it hands out a scratch card at the checkout register with a percentage discount concealed by an opaque covering. The customer scratches off the covering and reveals the amount of the discount. The table below shows the probability that a randomly selected card contains each percent discount. So here's the what, and here's the probability. What is the expected value, aka the mean, of the percentage of discount? So these being percents, we can work with them as numbers or percents. For me, it makes sense to just say, okay, 5% is a discount, 45% is the probability. Plus, there's a $10 or 10%, discount, and that has a 25% chance of happening. There's a 15% discount, and that has a 15% chance of happening. 25% discount with a 10% chance of happening, and a 50% discount with a 5% chance of happening. When you type that into your calculator, you get that there is a overall 12% expected discount. So big majority of the discounts are in that 5 to 10% range. That's what? 70% of all the discounts are in that 5 to 10 range. But we have a couple big guys up here that are pulling that expected value a little higher. You could also put this in your list. So this would be list 1. And this would be list 2. And then you would do one variable stats. We have not used 2 variable stats. You don't need to use that for the way we do things. So you do one variable stats. And your values, X list is in list 1. And your frequency list, you treat your probabilities. That's your frequency list. And then you calculate. Okay, onward. In basketball, an offensive rebound occurs when a player shoots and misses, and a player from the same team recovers the ball. For 176 players on the roster for one season of professional men's basketball, the third quartile, so the 75th percentile, for the total number of offensive rebounds for one season was 143. If 5 players are selected at random with replacement from that season, what is the approximate probability that at least 3 of them had more than 143 rebounds that season? Okay, couple things coming up. We want to know probability of at least 3 out of 5. Since we have that fixed number of trials and a boundary point, and we're going to have a fixed probability, that's going to be binomial. So we're going to say binomial CDF, because of this at least, right, is not exactly. We have 5 trials. The probability of anyone having more than 143 rebounds. So 143 is the 75th percentile. So 75% is below that, which means more than that is going to have a probability of 25%. Here's the kind of tricky bit. Binomial CDF is always going to give you the probability of this value and below. We want to know at least a number. So in order to get what's above, we're going to calculate the probability of what we don't want and then subtract it from 1. Because the probability of what we don't want plus the probability of what we do want should add to 1. So at least 3 includes 3. So we don't want to take out, we're subtracting this, we don't want to take out 3. We want to take out what's below 3. So we're going to put a 2 there. When we do that, we're going to get 1 minus binomial CDF, 5 trials, 25% probability, x value of 2, and we get 1035. Okay, good. And just to point something out here, when we've got these numbers in our answer choices and we're calculating them for the most part, we're doing the calculations, we're getting to a number. We're doing the calculations, we're getting to a number. Here, we're looking through each answer choice and reading it carefully and thoroughly. That's what a lot of you said you need to do on your test when we did our last test corrections, that you just need to read your answers more thoroughly. So make sure you remember to do that. Okay. 12. A new smartwatch is manufactured in one part of a factory, then secured for shipping in another independent part of the factory. The weight of the smartwatch has a mean of 62 grams and a standard deviation of 1 gram. The weight of the packaging, box, user's guide, bubble wrap, etc., has a mean of 456 grams and a standard deviation of 6 grams. Together, the distribution of the weight of the smartwatch and its packaging would have the following mean and standard deviation. Okay. So when we're basically combining means and standard deviations. So when we're adding the means, we can just add them. 62 plus 456, that's going to be 518. It's definitely not going to be 394, which is probably what you get if you subtract. Okay. Then, for standard deviations, this is where that Pythagorean theorem of statistics comes in. We're going to take the square root of the first standard deviation squared plus the second standard deviation squared. And that's going to be our new standard deviation. This is how you combine standard deviations, whether you're adding the means or subtracting the means, because adding a second component is adding variability, right? Think about how much more challenging it is to make plans with 3 friends than it is to make plans with 1 friend or 2 friends. So the more things you're adding, the more complications you're adding. So it's going to impact the standard deviation. So this is going to be root of 37, which is going to be just over 6. So we're not just going to this. I'm not even sure how you get 3.5. Oh, I guess if you added 1 and 6 and divided by 2. And then 7 grams would be if you just added the standard deviation. So that's definitely wrong. So we don't just add standard deviations. Great. So our answer is C. Moving right along. 13. The total cholesterol level in a large population. Let's try that again. Total cholesterol level in a large population of people is strongly skewed right with a mean of 210 milligrams per deciliter and a standard deviation of 15 milligrams per deciliter, I think. I'm going to also make a note that this is strongly skewed right. If random samples of size 16, that's important, are repeatedly drawn from this population, which of the following appropriately describes the sampling distribution of these sampling means? So the sampling distribution. So It's going to go from strongly skewed right towards normal, but not all the way to normal because the sample size is less than 30. So because the sample size is less than 30, not normal since parent population isn't normal. Okay. So the shape is unknown. No, that you don't know it. The shape isn't unknown. The shape is approximately normal. Nope, that's out. Shape is also not approximately normal. No. And the skew is not going to change from right to left. We're still going to have a right skew, somewhat skewed right. But because our sample size went up from 1 to 16, we're going to move towards normal. So we're still skewed right, but we're getting normal-er. The mean is going to stay the same. So the mean of the population is the mean of the sampling distribution. Now, the standard deviation must be this because we crossed out all our other answers. The reason why is, and this is on your formula sheet and it's in your formulas on the online system. When we have, this is the standard deviation for one. If we randomly pick one, as sample size goes up, variability goes down. And so the way we address that is say, here's the regular standard deviation, and then we're going to divide that by the root of our sample size. So this is going to cause our variability to go down as this number gets bigger and bigger. Okay, almost done with our MCQs, and I'll take a little cat break. In one metropolitan region, technical writers have an annual salary that is approximately normally distributed with a mean of 55,800. The first quartile of salaries is 48,815. What is the standard deviation? Okay, so first up, first quartile, 25th percentile. So we know our mean. We don't know our standard deviation. I suppose you could test your answer choices here. That's one option. That's a little bit inside baseball. Let's do the math. So we're going to say inverse norm. And we want the 25th percentile. Again, if you have a newer calculator, make sure you're picking left tail. Because we don't know both the mean and standard deviation, we have to default to 0 and 1. And this is going to equal a z-score. So we're going to say inverse norm, area is 0.25, mean, standard deviation 0 and 1 respectively. And we get negative 0.67. And this is our z-score. Now, the reason I put that dot, dot, dot there is we're going to end up with an answer choice, with an answer that's very close to another answer. You can probably figure out what it is, which two of the five it could be. You're not going to have something that's this close on an actual AP test. This is a kind of poorly written answer choice because you shouldn't be able to get one answer, be closer to one answer or another due to a rounding error. Okay, so this is our z-score. And then to find a z-score, we take our actual minus mean over the standard deviation. We now know 3 of these 4 variables. We know that the z-score is negative 0.674 dot, dot, dot. Just leave that in your calculator. Don't clear it out. We'll just pull it in a second. And then our actual was 48,815. Our mean is 55,800. And our standard deviation is unknown. Through the magic of algebra, which if you have forgotten, please do a little refresher. We'll do a little bit of that. We're going to get that the standard deviation is the difference here. So 48,815 minus 55,800. Negative 6,985 over negative 0.674 dot, dot, dot. Notice this is real close to that. So in your calculator, you're going to do this divided by, and then just scroll up to where you got this number after you did inverse norm. Scroll up until it's highlighted and then just hit enter. Your calculator will pull that for you and then it won't round. You only want to round once and you want to do that at the very end, not along the way, because you're just going to end up getting further and further from the right answer, basically. So when we do that, we get a standard deviation of $10,355.98, which is basically 10,356. I believe a lot of you rounded it at 0.67 right here. And when you do that, it ends up at 10,425, which is like technically closer to C and like very much in between these two, which again, not good question design. All right. Oh, you're going to make me do this one again. You know, I don't like these any more than you guys do, but I just understand that they're necessary. So, a local library has a scanner to detect library materials that have not been checked out. Each item has a chip somewhere inside. Upon checkout, the chip is deactivated, so the scanner has a 98% chance of detecting an active chip, meaning the material has not been checked out, and setting off the alarm. The scanner also has a 3% chance of sounding the alarm when someone passes through without an active chip. So, it's estimated that 0.5% of library customers actually try to leave the library with an active chip. What is the probability that, if the alarm sounds, the patron leaving the library has an item with an active chip? So basically, we can think about someone trying to leave the library with an active chip. Okay, someone's trying to steal from the library. What a terrible thing to do. The way to rephrase this is, given the alarm went off, what's the probability that you actually have a thief, that you're actually setting off the alarm because you're catching a thief? So we want to start with this. We want to start with how many people are going to have an active chip or not, or what percent. So 0.5%, so 0.005 are trying to steal. And that means that, oh, that's too many zeros, man. That means 0.995 are not trying to steal. If the person is trying to steal the book, there's a 98% chance of alarm. If there's a 98% chance of alarm, that means there's a 2% chance of no alarm. And we'll do the same thing here. If the person is not trying to steal, there is a 3% chance of alarm, which means there's a 97% chance of no alarm. And I'm okay with this getting a little messy because we're in a given situation, given the alarm sound. So we're only interested in pathways like this, where the alarm goes off, and like this, where the alarm goes off. So we want to know this pathway, and we want to know this pathway. So the probability that someone is trying to steal something from the library and the alarm goes off is 0.005 times 0.98. And that is 0.0049. The probability that someone is doing what they're supposed to and the alarm accidentally goes off is 0.995 times 0.03. And that is 0.02985. Okay. When we add those together, that plus this is going to be the probability that the alarm goes off at all. So first I'm going to add these together. 0.03475. Since this is a given situation, this is going to become our denominator, given that the alarm goes off. Alarm sounds. 0.03475. What's the probability that the person is actually trying to steal, that the person's leaving the library with an active chip? That was this. So we're going to do that. So given the alarm sounds, what's the probability the person is actually trying to steal? And we get, no, that divided by that, we get about 14% chance, which matches C. Okay. Two more. Which of the following is the best description of the power of a significance test? The power is the probability of correctly rejecting the null hypothesis. Not a whole lot of elimination to do. That is just what power is. It's the probability of correctly rejecting the null hypothesis. Cool. This rest of the stuff is other things. This is p-value right here. These are related, but not exactly. Like power is related to errors, but this is the definition of power. Memorize it. Last multiple choice. We'll take a little break. A producer of skincare products has created a new formula for its cream to cure acne. To compare the effectiveness of the new cream to that of the old cream, the company conducted a double-blind randomized experiment. Good, gold standard. Volunteers with acne tried the old formula on one side of their face and the new formula on the other, and which side got which formula was determined randomly. So this is an experiment, which means it's okay that these are volunteers with acne because the treatments were randomly assigned. The response variable was the difference in the number of pimples, old formula minus new formula. Which is the correct significance test to perform? Okay, so since we're talking about the difference in number, number is going to be about means. So it's not a proportion test. It's not a chi-square test of independence or a goodness of fit. There's not a certain proportion of pimples we would like, generally. Okay, so then the difference here between a two-sample t-test and a matched pairs t-test. Two samples would be one group used the old formula and one group used the new formula, and then they compared whether there was a difference in the average number of pimples between the groups. This is a matched pairs test because we have this very tiny block of one person, two halves of their face. So we're matching a person to themselves and then finding the difference. So this is a matched pairs t-test for a difference in means, or excuse me, a mean difference. This is a matched pairs t-test for a mean difference, an average difference, because we're actually running our test on the old formula minus new formula. So that's a matched pairs test. Matched pairs tests often compare either someone to themselves, or like twin studies are often matched pairs tests. You'll see that a bunch. All right. So now let's stop the share. And since I have heard from more than one person that this is a nice part of the videos, let's see a kitty cat. So here he is, resplendent, relaxing. I think he's too far away to get the full effect. So let's get this boy. He saw it coming and he was mad. Say hi, buddy. Say hi to your fans. I think he's in his happy place. He looks like he's dissociating. I'm sorry, buddy. Oh, no. Oh, dear. Goodbye.